Hello friends, welcome to my YouTube channel Obsession for Learning. Here I teach you step by step about design of structure manually and by using software. Okay, without doing delay, let's move to our topic. Today's our topic is about design of slab. Okay, as per IS 456 2000, which is corner not held down slab. Okay, here we have some of available data which is required for designing of slabs. You can see over here, such as depth of slab, which is represented by D, is equal to the 145 mm. Okay, and floor finishing load, which is 1 kilonewton per meter squares, live load, which is 3 kilonewtons per meter squares. Similarly, dead load, we have to calculate these ones. This is the 25 is nothing but it is the unit weight of RCC slab, you can see here, and I'm multiplying these ones with the depth of slabs. Okay, 0.145, it is in meters. Okay, so by multiplying these two value, I'm getting here 3.625 kilonewton per meter squares. Okay, like this way we can calculate the dead load of slab. And here you can see the FCK is nothing but it is the compressive strength of concrete, which is 25 newton per mm squares. Similarly, you can see here Fy, which is also L strength of steels, it's 500 newton per mm squares. And Lx and Ly, Lx is length along x-axis and Ly is length along y-axis. It is the dimension of slabs. And Lx, which is 2250 mm, and Ly is 4500 mm. So it means our shorter span is Lx and longer span is Ly. Okay, we can easily distinguish from here. Now at step number 1, we can calculate the effective spans at first. Okay, so here we have formula effective spans along x-axis, which is represented by Lx. So it is nothing but Lx plus d effectives. Okay, similarly effective spans along Ly, it is also like Ly plus d effectives. Okay, now 2200 plus d. Okay, by substituting the value of d, we are getting here 2395 mm. Similarly, here you can see by substituting value of d, we are getting here 4645 mm. It is the effective spans along y-axis. Okay, at step number 2, here we're going to calculate the moment. Okay, you can see here's the total loads is nothing but a floor finishing load, live load and dead load. The summation of these three loads, we're getting here 7.625 kilonewton per meter squares. Okay, for factor loads, we're going to multiply these total loads by 1.5, then we'll get the 11.4375 kilonewton per meter square. Okay, after that we're going to calculate the moment along x-axis and y-axis respectively. Okay, for that you can see here the moment calculation formula, which is mx is equal to alpha x wf L effective x square, right? So similarly for my, you can see alpha y wf and L effective s square. It means it is the constants, and this is wf is the factor load, and L effective x is effective length along x-axis for both moments. Okay, along x-axis and along y-axis. Okay, look at here for that constant value alpha x and alpha y, which is 0.118 and 0.029. I have taken this value from the IS 456 2000 table number 27. Okay, yes, and by putting the values of values on this formula, we are getting here 6.884 kilonewtons meters and my as 0.75 kilonewton meters. Okay, at step number 3, what we have to do is we have to check for the depth. Okay, we have here one formula. When the xu d is equal to xu limit by d, or we can take xu by d as 0.46 for Fe 500, then we can use this formula, right? So I am using this formula just for calculating the d, which is d requires. Okay, and for Fe 500, mu limit is equal to 0.133 FCK BD squares. This is the relation we have taken from the SB16 code as well. Okay. Look at here, so d effective required is we get 45.35 mm, right? So which is less than d effective provided, so it is okay, it is safe. Okay, our provided depth is greater than the required depth, so it is okay. So notes, provides effective depth is 105 mm, and overall depth is equal to 125 mm respectively. Okay, now at step number 4, what we have to do is area of steel along the shorter spans. You can see here Lx. Okay, Okay, for under reinforced sections, here we have formula for calculating the area of steels. Okay, we have been calculating this area of steels along shorter spans, which is ASTX. Okay, so by using this formula. Okay, now by putting the value of dfy on this formula, or as fy bd fck on this formula, we're getting here 154.36 mm squares, right? So this is our AST required, you can see. Okay, according to the codal provision, you can see our minimum area of steel required should be 0.12%. Okay, by calculating this value, we are getting 150 mm square. So if you see here, our required ASTX is 154, so which is greater than minimum minimum, you know, like area of steels, right? So it is okay, our shape, you can say. Now I'm using 10 mm bar. Okay, for 10 mm bar, the area for individuals bar, which is pi d square by 4, so simply it is 78.54 mm square, right? Now for spacing, it is nothing but it is the ratio of area of one individuals reverse divided by the area required into thousands in mm, but for we are checking for 1 meters. Okay, so we are getting here 508.81 mm, but I'm adopting here 150 mm, right? So now what I have to do is I have to again calculate the provided area, because I have adopt the spacing as 150 mm. I'm not doing anything here, I'm just replacing the value spacing and then area. Okay, for now I'm calculating the area, so it means I'm providing the spacings over here. Look at here, and simply I have got here 523.6 mm square, which is greater than AST required, so it means it is safe. Okay, now provide 10 mm bar along x-axis at 150 mm center to center spacing, and this is just for the short spans. We're gonna calculate for the longer spans in our next video. Okay, if you guys find my video is helpful for you guys, please don't forget to give thumbs up, subscribe my channel, hit the bell icon for getting notifications. Okay, and at last, if you guys have any confusion and difficulty, please leave the comment in the comment section. I'll like make video according to your comments, just for helping you guys. I'm just making videos